Here we got website 5, problem number 13. This one, this problem is going to utilize momentum and conservation of energy. So here we go. Two blocks of masses M and 3 are placed in frictionless horizontal surface. The light springs attached to a massive block, and the blocks are pushed together with a spring between them as shown in the figure below. A cord initially holding the bricks together is burned. After that happens, the block of mass 3m moves to the right with a speed of v sub 3m is equal to 2.3 meters per second. Okay. So you got a picture here. So after, obviously it shows it right here. Yeah, after the movement, it's gonna go this way. This one's gonna go this way, and that's gonna be important for when we say right now. This is gonna be our, I like red. Okay, that's gonna be our positive direction. So whatever this speed's gonna be, it's gonna be negative, and this one is going to be positive. All right. What is the velocity of the block of mass m? Assume the right is positive, less negative. Okay. So here I'm going to utilize momentum because we're giving a mass and we're giving a velocity. So P is momentum. So P is going to equal to P. But now, what do these P stand for? So we're going to P1 and P2, just so it's makes sense. Okay. So our P1 is going to be this block. This is going to be our P1. And our P2 is going to be this block. All right, and we know the momentum, so we're just going to M1 V1 is equal to M2 V2. Okay, and now we're going to have to plug in what we have. So mass 1 on this side is just M. V1 on this side is unknown, so we have to give it V1 equal to mass on this side is 3M. And its velocity is given right here at 2.3 meters per second. Okay, and then we're solving for, what is the velocity of the block of mass m? So we're solving for this velocity. Okay, so we can, v1 is going to equal 3 over m, or not 3, okay, 3m times 2.3 meters per second over m. These will cancel. v1 will equal 3 times 2.3, which is 6.9 meters per second. But if we look at what we describe as positive, and that's this direction, these two directions are positive. So this way is positive. This block, as you can see by this arrow, is going the opposite way. It's going this direction, so we have to flip the sign. So it's actually going to be negative 6.9. Alright, find the system's original elastic potential, taking m is equal to 0.360 kilograms. Sorry. Excuse me. Alright. Jesus. Alright, okay. This one's going to utilize elastic potential energy. Okay, so we have to use conservation of momentum, or conservation of energy. And because we want to find, so we already know we have to find elastic potential. So U is going to equal something. And if we look at the amount of movable parts we have the spring, which is going to be our potential. Then we also have this box, and we have this box. So it's actually going to be two kinetic energies we're going to look at. We're going to look at kinetic energy because they're moving, they have velocity. So it's going to be U is equal to KE plus KE. Or it could just be like U is equal to sum of KE. Alright? And it gives us the mass, so we can plug it in and find the elastic energy. So U is equal to, kinetic energy again is 1/2 mv squared, mv1 v1 plus 1/2 m2 v2 squared. Now I can plug in our values. So U is equal to 1/2, and again 0.36 is going to be our value of m, and our m1 mass is, well, just m, so it's going to just be 0.36 kilograms times its velocity, which we just solved for, which is 6.9, and we do not have to include negative here. We do not have to include negative here. Or we not have to, we don't include negative here. Squared plus the kinetic energy of the other block. And this one's mass was 3m, so 3 times 0.36 is 1.08. by its velocity, which was given to us, which is 2.3 meters per second squared. So U is going to be equal to about 8.568 joules, because it's energy, so it's going to be equal to joules, plus 2.8566 joules, and then that's going to obviously equal 11.42 joules, and that's our answer, 4.4264, depending on how far I go. All right, now, question C. Is the original energy in the spring or in the cord? So now let's think about how we interpret this. So the string is broken, and then the process occurs. So if anything, the string is what's like keeping what's not allowing the energy to be released. So it's not the one holding it. That means the spring has to be the one holding, because when the rope, we'll say it's like a blockade. When the blockade is removed, then the movement can occur. And if the rope is the blockade, then the rope is not the one causing the movement. So that means the spring is, which is the one who ends up causing the movement down here, because the rope is stopping it. It's not that the rope has the energy; it's that the rope's not allowing it's not allowing the blocks to move because it's holding them together. So, in theory, the tension in the rope would be equal to the energy in the spring, because it's obviously not letting it move. So the second the rope, the blockade is removed, the movement can occur. So it would be in the spring. The answer would be in the spring. And then I explained why. Is the system conserved in the bursting apart process? Okay. Yes. Explain that as possible. Okay. So we're on a frictionless surface, and it's horizontal. So there's no angles. So gravity's only working this way. Gravity's not working at an angle, causing deceleration or acceleration in any sort of way. We're not looking at air resistance, so air resistance is not going to cause anything. We're not looking at, there's no friction, so it can't be lost during heat. In this context, explain how it's possible, because there's no motion beforehand and plenty of motion afterward. So the spring is holding all of our energy, and we just found that this is what the spring energy would have to be to cause the velocity change from, well, not the velocity change, but like to cause the block of lesser mass to go that fast and the block of heavier mass to go as fast as it did. So the spring, the energy is all in the system. It's just stored elastically. The rope is broken, aka the blockade. The spring is released. The spring releases its energy into the form of the movement of the kinetic energy of the blocks. So I'll explain how, because there's no motion beforehand. Well, like what I just said, there's no motion because the rope is forcing there to be no motion, because it's stored in the spring, being stopped by the rope. When the rope breaks, the spring can expand and release its energy into the blocks. So the energy is always there. It's just not moving because of the rope. Yeah, so this one's those problems where you can combine momentum and energy. It's really nice when you get the right answer, I'll tell you that much. It's just like, wow, I know what I'm doing. Common mistakes, I mean, you probably, if it makes a brain fart, like you might just, like the 3M might throw you off, like, wait, there's no actual mass, it's just like a variable. That might throw you off. Just work it through like you would a normal, just like put in your momentums, then plug in your values, and then obviously it'll work itself out. So just like trust like in what you know how to do, trust your basics. And yeah, that's how you solve web design 5 question number 13.